Thank you all for coming. I'm Venkitesh. I'm a postdoc in the computational cosmology group at CRD, and I'll be talking about my research on signal background classification in particle physics experiments using convolutional neural networks. And the title in simple words is Machine Learning Can Make Computations in Particle Physics More Efficient. The talk has three main pieces. The first part is describing the signal background classification problem in particle physics. Then I'll describe convolutional neural networks, or CNNs, which are used for classification. And finally, I'll talk about our application of CNNs to particle physics data. The goal of particle physics is to understand what we're all fundamentally made of. And we now know that everything around us is made of a few particles put together in different ways. This is called a standard model of particle physics, and it has these particles and these four fundamental interactions, and it explains the world around us very well. Over the last century, all these particles have been discovered, and many of these have been given Nobel Prizes, and most latest being the Higgs boson in 2013. However, there are some discrepancies, and these point to the possible existence of new particles or new interactions. And as a result, there are many particle physics experiments looking for new particles and forces. Some of the proposed particles are dark matter, axions, etc., and many theories, for example, supersymmetry. And there are many experiments, for example, the Large Hadron Collider at CERN, which found the Higgs boson in 2012, but it's still looking for other theories such as supersymmetry. There are dark matter detection experiments like LZ in South Dakota, and again, many, many more. A lot of these particle physics experiments have the same recipe to find new particles. You have particles coming in, either you generate them right there or they come in from space, they interact to produce other particles which are detected, and from that you try to interpret what the properties of the incoming particle must have been. Now these experiments, turns out they produce a lot of data. The LHC generates about a gigabyte of data per second. That's about 25 petabytes a year, which is huge. And it turns out most of this information is from physics that we know and understand pretty well. And this is what we term as background. Now contrast this with the physics that we want to find out, the new physics. Turns out this shows up in rare events, and this is what we term as signal. To give you a rough idea, to the right you have this picture from the famous Higgs discovery paper. This is the Atlas paper, where you can see all these points, data points that correspond to number of events on the y-axis and mass on the x-axis. The interesting part here for the Higgs is this region right here above the blue histograms. And as you can see, while that is the interesting part, there are so many events to the right. And so for the study, that is the signal. And as a result, we need to find a way to distinguish signal from background. And this is the signal background classification, and it's an important part of for any particle physics experiment. The current method to do this is by performing cuts on data, and this is guided by either theory or simulation. And while it works pretty well, the drawback is we could be throwing away potentially interesting data. So the question is, can we use machine learning classification techniques like convolutional neural networks to make this better? Just a brief description of convolutional neural networks. We know that neural networks are computing systems that are very good at learning patterns in unknown data. Convolutional neural networks, or CNNs, are a special class of neural networks that specialize in image recognition and classification. The way they work is the following. You feed the CNN images. Images in the real world pictures it's just a matrix of pixels, which is basically a number matrix. The CNN is trained on known labeled data, and once it's trained correctly, if you give it an unknown data, it can tell you what category of image it belongs to. And CNNs have been extremely successful in many classification problems. For example, handwriting recognition, where you have handwritten digits 0 to 9, and the CNN can tell you precisely which class it belongs to. Distinguishing pictures, for example, cat pictures and dog pictures, and many other problems. I'll quickly describe the general structure of a CNN. CNNs there are many types, and some of them are extremely complicated, but they typically have certain standard blocks. They often start with a convolutional layer, whose main purpose is to map high-level features from the image. These convolution layers make the dimensionality quite high at that layer, and the dimensionality is reduced by what are called subsampling layers. Typically, these two layers are repeated for quite a few times. Eventually, you have what are called fully connected layers, which combine them together, combine the parameters at a single layer, and then you have an output, which then gives you which class it predicts the image to belong to. So how are we going to use CNNs to solve the signal background classification problem that we have in particle physics? As I said, CNNs take in an input image, which is a matrix of numbers, which could be pixel values in a picture, or it could be measured quantities in a detector which has some kind of spatial arrangement. So the procedure we'll follow is the following. We'll feed the CNN a labeled data set. That's a data set where we know what is signal and we know what is background. And in this work, we'll use simulation images, and we train the convolutional neural network. And if the training is successful, then if we give it another data set, it should be able to predict correctly whether it's signal or background. The question is this possible? Now, in this work, we develop multiple CNNs and compare their performance. And the way we do that is by looking at the ROC curve, known as or receiver operator characteristic curve. As I told you before, the CNN, the output of a CNN is the class which it belongs to. But actually, what it gives out is a floating point number. So for the problem of just two classes, let's say signal and background, where signal is characterized as 1 and background as 0, the CNN will give you a number between 0 and 1. And the way we assign a class is by using a threshold. So for example, if the CNN predicts the number of 0.4, if you have a threshold of 0.5, then that will be classified as background. But if you put the threshold as 0.2, now it will be classified as signal. So this is what a ROC curve looks like. A ROC curve has false positive rate on the x-axis and true positive rate on the y-axis. In this problem, false positive is when you classify a background as a signal, and true positive is when you classify a signal as a signal. So clearly, what we want is a low positive rate and a low false positive rate and a high true positive rate. So these are ROC curves for two different models, and the way to understand this is every point on the ROC curve corresponds to one threshold. The typical way to compare, if we have multiple models and we want to see which one is doing best, one way to do that is to fix a reasonably low false positive rate, and then look at the two curves. The curve with the higher true positive rate for that is the one with the better performance. And this is how we'll be comparing our models. Having discussed CNNs and the method we're going to use, now I want to discuss the first data set that we used, and that is from the IceCube experiment, which is a neutrino observatory based in the South Pole. It is searching for cosmic neutrinos, and neutrinos are extremely light and weakly interacting particles that bombard the Earth. IceCube has an array of what are called digital optical modules. They're placed below the Antarctic ice, and they're almost a cubic kilometer in volume, so it's a very huge detector. And the way it works is these cosmic neutrinos interact with the ice to produce charged particles, and these radiate to give light, which are then captured by these called domes. Now I want to talk about for this data set, what is a signal and what is a background. As I mentioned before, cosmic neutrinos interact to give charged particles. For this data set, we consider just one type of charged particle called muons. Now, the signal here is muons generated by these cosmic neutrinos. And here's a picture. Try to think of it as a three-dimensional picture. This is a picture of where the line there is the path of the muon. The blobs here correspond to intensity of light. And so this denotes the path of a muon passing through, and at that particular point it radiates a lot of light. And it turns out for these signal muons, they're often just very few in number, typically just single muons. As a result, you would have a picture like this for a signal, where it will radiate a lot at one particular point and very little elsewhere. To contrast this with the background is any other source of muon other than from these neutrinos. And the most dominant source of muons are atmospheric muons. It turns out these atmospheric muons are typically very large in number. So you'll have a shower and you'll have hundreds of them. And in that case, what will happen is, as a bundle, they'll radiate light at different locations inside. As a result, you'll get multiple blobs like that. So the job of the CNN is to distinguish signal from background when the images sort of look like that. Now, the data set, as I mentioned, is with 3D images, and the input is the light intensity and the time at which each optical sensor gets that event. And there was work done on this data set before by Choma and all, where they studied a lot of machine learning techniques, GNNs, CNNs, etc. And for CNNs, they found a model called ResNet that did pretty well. However, these ResNets have a very large number of parameters. And the problem with having CNNs with a lot of parameters is you could be overtraining, and as a result, you'll have a model that works but does not generalize. And also, ResNets are optimized for real-world pictures. So the goal of this work was to develop low-parameter CNN models. So the procedure we followed is the following. The goal was to develop CNNs by stacking these blocks of these layers together. And we started off with a few models varying some of the parameters there, and we picked up some of the best models that worked, and then we varied some of the parameters even more. And overall, we tested about 30 models. To give you an idea of the procedure followed, here's a simple model that we use that you see to the right, where you have the input and then you have convolutional layers. You have max pooling, which is a subsampling operation. You had dropout, which is a way to reduce, to prevent overtraining. So we had blocks of that continuing through. And in this case, this is a very simple model, but obviously we tried a number of models with much higher number of parameters. So now I'll show the results. Here is a ROC curve with for three models. We have one that is called compact CNN, which is the best model from our work. We have something here called ResNet, which is the best model from the previous work. And then we're comparing it with a very simple CNN. As you can see, for a fixed value of false positive rate, here this vertical line, you can see that the compact CNN has a higher true positive rate than the other two. And it's consistently higher throughout the curve, which means the compact CNN is performing much better than the other two. Here we have a table with some of the parameters for these models. The first column shows the number of parameters. As you can see, ResNet had 26 million parameters, and the compact CNN has just 2 million. And so the conclusion here is that the compact CNN is performing better than the ResNet, and it only has a tenth of the parameters, which is what we wanted. We're also comparing it with a very simple CNN just to make sure that there aren't many more. It could well be that there could be even simpler models. So we've explored quite a few, and we found that simpler models may have lesser parameters, but they don't do quite well. The second column has the time of training per epoch on a GPU. And there we see something a little bit anomalous. Typically, you would expect a model with high parameters to have a higher training time. But here we find that ResNet was actually a little bit faster than our compact CNN. And while we don't understand why that is, one possibility is that ResNet, since it's such a specialized network, it is complicated but has so many connections, maybe somehow that's making it a little bit faster. Nevertheless, in this work, the model that we've developed has a better performance and has a tenth of the parameters of the previous model, which is definitely a success. And in the previous work, they had shown that their CNN ResNet was performing better than the physics method. So our model is definitely performing better than that too. Now, to establish generality, we also studied this with a totally different 2D data set from the ATLAS experiment. This was a data set that was used in an analysis for searching for massive supersymmetric particles. And again, here, there was previous work done on this, where they had studied CNNs and shown that they do pretty well compared to the physics method. The goal here, again, was to explore the CNN architecture and find models that do even better and have lesser number of parameters. As you can see in the left figure, this is again a ROC curve, where you have compact CNN, which is the best model in this work, compared to the old CNN that's in the previous paper. And we also just compared it with ResNet, but ResNet doesn't do very well here at all. What you see here is for a low false positive rate, again, the compact CNN does better than both models, telling us that it has the best performance. If you look at this table, you can see first in the first column the number of parameters. The old CNN has 34 million parameters, which is a lot. And our best model, the compact CNN, has only 43,000. So it is significantly better. It has, what I say 100th, it's almost 1,000. It's significantly better in terms of number of parameters. And also the time of training for this model is significantly lesser than the other two. So even here we find that these stacked CNNs do surprisingly well. And during the course of this work, we were scanning the CNN space, not exclusively, but we were testing quite a few models. So we developed a package to explore different CNN architectures. And we also developed visualization tools with Jupyter notebooks for viewing the training and performance. To summarize, I've discussed the use of compact CNNs for signal background classification. We've demonstrated their success for two different data sets, improving upon previous work. But we've only done this with simulated data. We've developed a package for general CNN training. And given that CNNs seem to do a good job with signal background classification with data from these experiments, there's potential for their use in other fields beyond particle physics. I'd like to acknowledge my collaborators, Wahid, Nick, Zara, Sally, and Lisa. Thank you.
So for the ATLAS data, you said you use 2D images. Are these 2D images of the actual particle tracks in the detector, or?
That's basically, no, this is just, the energy deposit on the calorimeter. Oh. So it's a simpler data set. Yeah.
Can you go into a bit more detail on how you varied between the architectures? Was it like a random scan of different parameters and architectures? Or?
Well, it was a mixture of intuition and seeing which ones worked best. Obviously, typically when you do an architecture search, you get you get a lot of things that don't work, let me go back to that slide. Yeah, so typically the approach is you try a few layers, you vary the kernel size based on some, like you look at the images and kind of get it. For example, you won't have very large kernel sizes, and So initially you perform like 4 or 5 different, and you can clearly see some doing much better, and then you perform further variations on that. But this is by no means a complete architecture search. You can definitely maybe go and come up with a model that works best. But the idea here is that something just stacking layers together, you can beat something like ResNet, which is so complicated and took so much effort to design.
So for ResNet, you can specify the number of layers. So have you compared ResNet with a small number of layers? So how does that compare to your compact CNN?
The ResNet we used was ResNet 18. I don't think we explored a few, I think ResNet 50, but we didn't explore it that thoroughly. But in the previous work, they'd shown that ResNet works, which itself, I guess, is a kind of a surprise because it's designed for real-world images. So the goal here was just to make something simple and stacked beat that, and it seems to be doing pretty well.
Okay, thanks very much.